Okay, now here comes second theorem of the first chapter, that it's similarity. Okay, and the name of the theorem is the property of an angle bisector of triangle. We also call this as angle bisector theorem. Okay, so here by the heading of the theorem, you can understand that there is angle bisector in the theorem and in the diagram also. So for that, what the statement is, the bisector of an angle, the bisector, you know that what is bisector is? Bisector of an angle is nothing but the ray which bisects the angle into two equal parts, isn't it? So if suppose this is initially, suppose this is any angle which has its measure of suppose 50 degree, and there is any ray, if I draw like this, suppose I'm saying, and then I'm making marks like this on both the angles, so you can understand that this and this, both the angles are of same measure. That means it must be of 25 degree and it must be of 25 degree, because this initially was of 50 degree, isn't it? So this is how a bisector means. Okay, now what the statement is saying, the bisector of an angle of a triangle divides the sides opposite to the angle in the ratio of remaining sides. What is, what does it mean is, suppose there is any angle, any triangle, and it has any bisector of one of the angles. Suppose this angle is being bisected by this ray, suppose, means this angle is congruent with this because it is bisected by this ray. So what does that mean? The statement is, the bisector of an angle divides the side opposite to the angle. See, if you draw this bisector like this, the bisector divides the angle, isn't it? But it also divides the side opposite to this, to the angle. Side opposite to this angle is side this, isn't it? So this side is also divided by that bisector into two parts, like this and this one, isn't it? So what is statement saying is, the bisector of an angle of triangle divides the side opposite to the angle in the ratio of remaining sides. Means the ratio, if you take a ratio of these, it comes equal to the ratio of these remaining sides. The ratio of side divided due to this bisector is the ratio of these two segments, and it comes equal to the ratio of these remaining two sides of the triangle. This is what the statement is saying. So for to prove this, we'll have a diagram of triangle like this. Suppose I'm having like diagram like this. Suppose this is triangle ABC. Okay, and then we'll have to take a bisector of one of the angle. So suppose I'll bisect like this. I'll bisect angle C, so that this angle and this angle are of same measure. Okay. Now, whatever the diagram is, we have to take the considerations into the given section of the theorem. So I will write all over here. In triangle ABC, this ray, suppose I name it as CE, ray CE is an angle bisector of angle ACB. Okay, ray CE is angle bisector of angle ACB. Okay, now this is I have taken in the given section. So I can say that angle ACE and angle ECB are of same measure, isn't it? Angle ACE, because the whole angle C is bisected, so I can say that it is equal to the sum of the two parts, isn't it? So angle ACE and ECB are congruent. Okay, since they are being made by bisector, so they must be are of same measure, ACE and ECB, ACE and ECB. Okay, now this I have given it as equation number 1. Now what we have to prove is the ratio of these two segments should come equal to the ratio of remaining two sides of the triangle. So what I have to write here is AE by EB must be equal to AC by CB. A ratio of these two must be equal to a ratio of remaining side, that is AC by CB. So this is what we have to prove. Okay. Now again, to prove this, we have to again make some same construction. So for that, what I have to do is I have to draw, say, you know that this theorem comes after the theorem of basic proportionality, isn't it? So it does means that you have to use BPT to prove this theorem. And you know that we can only use BPT if there is a triangle with parallel line to one of the side. So in this triangle, there is no any line which is parallel to one of the side of the triangle. So to be useful BPT theorem, to be useful in this theorem, I have to draw one of the line to parallel to one of the side of this triangle. So I have CE, ray CE here, and what I will do is I will draw a parallel side to CE, and I will draw it from B. Okay, so for drawing a side parallel to ray CE, I will draw this like this, and I will extend this AC again so that it can meet this side at point D. Okay, now these two CE and BD are parallel. Okay, so now you can see that if you just keep this side CB like this, then you can see that in triangle ABD, CE line is parallel to side BD. So it is useful for us according to BPT, isn't it? See, if you just wipe out that side CB, if you just wipe out that side CB, the triangle is like this. Here it is C, here it is E, this is A, this is B, and this is D. In this line, CE is parallel to BD. So by using BPT, what we can write is AE by EB equal to AC by CD, isn't it? But according to BPT, we can say that these two ratios are equal, and we need AE by EB equal to AC by CB. Instead of CD, we have to get CB. If you get at this side instead of CD, if you get CB, then you got proved this theorem, isn't it? So to make here CB, we have to understand from figure what we shall do. Okay, you will come to know further when you go through this theorem. You will come to know how it is, how easy it was actually. So now I will write that construction part in the construction region. What we did is we just draw uh, side parallel to We just draw a side parallel to CE from B, isn't it? From B, and we extended AC up to D. We extended this AC up to D, and then BD becomes parallel to CE. Okay. Now we'll have proof. So, what is there? Okay. Now, see, in this triangle, in this triangle, A B D, in this triangle, if you take AD as transversal and CE in BD as parallel, if these two are parallel and CD or AD is transversal, then what we can say is, like suppose I'll draw this again. See, these two are parallel. One of these is CE and another one is BD or DB. And if you take this as transversal, okay, which is AD or AC, extended AC. Okay, so what we can say is these two angles are same, or these two angles must be congruent. Why? Because these two are parallel and this is transversal. So these type of angles are corresponding angles. So if two lines are parallel, then corresponding angles made by a transversal are congruent, isn't it? This we know that we have learned in standard 9, in previous standard, isn't it? So we'll take that first. So CE is parallel to BD and AD is a transversal. So what we can write is angle ACE is congruent with angle CDB, isn't it? Angle ACE is congruent with angle CDB, means this angle will be congruent with this angle. What should be the reason? The reason is corresponding angles. They are corresponding angles, and we know that corresponding angles are congruent, isn't it? Now again, CE is parallel to BD. And suppose I am taking CB as transversal. Now again, I will draw a diagram over here. So this is CE and this is BD. These two are parallel. And if I take transversal like this, suppose it is CB, then what can I say? I can say that this angle and this angle is congruent, are congruent, isn't it? Why? Because they are alternate angles. So if C is parallel to BD and CB is a transversal, what I can say is angle ECB is congruent with angle CBD. Why? Because they are alternate angles, isn't it? If two lines are parallel, then angle made by their transversal are alternate angles and they are congruent, isn't it? Now if you see, in equation 1 there is angle ACE, in equation 2 there is angle ECB, and I have to write here as 2 and here as 3 because I have given there equation number 1 already. So now if you see in equation number 2 and equation number 3, there are angle AC and ECB which are already congruent with each other in equation number 1. So if you use this equation number 2 and 3 in equation 1, what I can write is these two triangles must be congruent because these are congruent, so these must be congruent. So from equation 2 and 3, equation 1 gives that angle CDB is congruent with angle CBD, isn't it? These two were congruent, so I have to write this symbol at this place also. So what we got is angle CDB is congruent with angle CBD, means these two are congruent. We got these two congruent in triangle CDB, isn't it? See, you can see that these two were congruent with each other. It was given in the statement. One of these was congruent with this. One of these was congruent with this. So we can say that if these two are congruent, then these two must be congruent. Isn't it? From figure also we can say that. This we have derived, but we can figure out it from figure also. So what we got here is these two triangles in this triangle CDB are congruent. Now you know that if two triangles, if two angles of a triangle are congruent, if any two angles of a triangle are congruent, then we know that the sides opposite to those two angles must be congruent, isn't it? I mean, if this CBD is congruent with CDB, then what I can say is side opposite to this angle is CD and side opposite to this angle is CB. I can say that CB and CD must be congruent. So I can say side opposite to CDB is what? It is CB. And side opposite to CBD, side opposite to CDB is CB, and side opposite to CBD is CD. I can say that these are the sides opposite to congruent sides. Sides opposite to congruent angles. Side opposite to the congruent angles are congruent, isn't it? If these two angles are congruent, then their opposite sides must be congruent. Now, remember, while proving this theorem, initially I did wrote here uh, the ratio of two sides by using BPT, and at the ratio there was one place which we were thinking about putting AB instead of CB instead of CD. Remember that? So here you got CB and CD are congruent. So again you will have to use that BPT in this triangle. So in triangle ABD, C is parallel to BD. So in any triangle, if one of the line is parallel to one of the side, then what we can write is AE by EB, that is ratio of this side must be equal to ratio of this side. It is equal to AC by CD. Now this CD we can replace with CB, isn't it? This was by BPT. So we have to change here CD with CB from equation 4, and this is nothing but our aim, isn't it? AE by EB equals to AC by CB. We got the aim. Okay. Now how to remember this? Initially you have to remember the statement. What is the statement is? The bisector of angle of a triangle divide the side opposite to the angle in the ratio of remaining two sides of the triangle. For that you have to take a diagram, you have to draw a bisector of any angle, and then you have to mix little construction that you have to draw a side parallel to that bisector. Okay, so that you can use BPT in the proof, isn't it? Then while proving, you have to consider first corresponding angles, then you have to go for alternate angles, and in the given section you already have the two angles which were being bisected are congruent. So by using equation 1, 2 and 3 you can have um, a triangle which has two angles congruent, and the sides opposite to those two congruent angles must be congruent. So you can use those two sides in BPT. Okay, just go through it. It will be easier for you. Just read it louder and just write it down for uh, one or two times. It will be easier for you. Okay, if you like my teaching, if you like my video, then do like, and don't forget to subscribe the channel. Okay.